the local version of the first law of black hole mechanics. And there is a global one, the one I described, that delta M that you see there is the variation of something called the ADM mass, which is a property of a space-time. You can say that a space-time has mass m, but you may not be able to localize it. Oh, there is 1% of mass here, half a percentage there, and I want to integrate everywhere, I get m. This is in general not possible in general relativity. And that's the m that appears in the Berdeen-Carter version, which is the global version of the first law of black hole mechanics. But even before that, Hawking and Hartle had worked out a local version of it. Now delta m is the energy that enters this tiny little surface of the horizon of a black hole. And then you integrate it. So the idea is you start from the equations describing how neighboring curves of which the horizon is made of behave as you move along the fine parameters, and you see how they, so you just linearize these equations, use Einstein's equations, assume that the black hole eventually settles down, and you integrate. And you get something that calligraphically is the same as Berdeen, Carter, and Hawking's first law. What turns out is that both versions admit a semi-classical generalization if you replace Einstein's equations by a semi-classical version of it. Here I write the global version in an intuitive way. If you start from, if matter outside is in thermal equilibrium with the hole, then it looks like a T, temperature, times the variation of the sum of entropies, of the entropy of the exterior, and the entropy of, well, the entropy that appears in the laws of black hole mechanics, the Bekenstein-Hawking entropy, that's the sum of them, then you get the variation of the energy as measured at infinity.
So where's the h bar in this equation?
Well, there is an h bar here in the temperature. Yes, that's right. Yeah, the temperature is proportional to h bar. That's right. Not on kappa. Kappa is a purely classical thing. Yeah. Well, you've got, yeah, okay, good. That's great. So this is a quantum mechanical object, but it's subject, I mean, there is an h bar here, then there's 1 over h bar in the entropy when you make this identification. But this entropy is the von Neumann entropy, how you calculate it. And you might complain that it's infinite, but this is just variation. So, well, I'll come back to that in a second. So that's a nice remark.
I have a question.
Yeah.
So this is an hypothesis, this is not proven, is it?
This is proven, yes, this is proven.
So you have there's a proof that the entropy outside the black hole plus the entropy of the black hole always increase.
No, well, this is the first law. So this is just relating the change in area, the change in entropies to the change in the energy in the end.
Yeah, but if delta is 0, so you have a isolated system, the total entropy always increase. I see. I'm sorry. I'm sorry.
Yeah.
My fault.
Well, but here's come the second law. Here comes this generalized second law. So the answer is still positive, but that's what I'm about to explain. Again, there are two versions of the second law. One, the local one is not very interesting. It's basically the same idea, but you assume positive energy, and you get non-decreasing areas. The global version, which is the area theorem that I mentioned in the beginning, it's much more interesting. You do need to assume some positive energy conditions, plus some global conditions. But it's valid, but then the change in area is that global thing that I told you about. So it's valid for black hole mergers, whose gravitational waves we detect on Earth. No local version can capture that, right? Okay, anyway, but this is the classical, for the classical laws, you need positive energy. So So this is saying that the area doesn't increase, but that's not what's verified in semi-classical physics. And that's a bit more work to prove in semi-classical theory than it is the first law, but there are proofs. So the local version was generalized by Aaron Wall in 2012, and I generalized a global version in 2020. And the results hold. I'm about to say a little bit about what you need to assume in a second, but let me just state that it has been shown. It's exactly what George was describing. It's the sum of the entropy of the exterior plus the entropy of the black hole is only the sum that ought to be non-negative. So you can have a decrease in area at the expense of increasing the entropy of the exterior. Okay, but so let's just spare some moments saying what these hypotheses are. And I think they are interesting because at this point we all have this urge to find an interpretation for these laws, for the entropy in terms of some microscopic physics. And a common ingredient for both versions is something that I can explain in words with an interpretation. So if you have a probability distribution function, and you evaluate the entropy function of the probability density function, you may construct from any one. If you have more than one random variable, you can find just the distribution describing a subset of these random variables by a process called marginalization. So you may not care about all the random variables. There's a subset of them. And if you do that, you can't possibly know more about the system than you knew before. So the entropy cannot decrease after this process. In the language of density matrices, you can say that the von Neumann entropy of a reduced entropy density matrix cannot be smaller than the von Neumann entropy of your original density matrix. Of course, we can't apply that immediately to quantum field theory because these things are infinite. But they are infinite for a very... We know exactly why they are different. That's because they are the UV behavior of states in quantum field theory. We know quite a bit of them. And we know they're always the same. So what we can do is what in probability theory, we introduce a prior. Or in density matrix languages, we pass not one state to the entropy functional, but two. And what this thing is measuring is how alike they are from one another. So if you do the partial traces of generalization to two distributions, so your prior and your final probabilities, or your two density matrices, they must look closer together. They must be more alike than they were in the beginning. So this is what this inequality is saying. So you need to use that. Well, yeah, I can comment more about that later, but let me not get into that because I'm starting to get short on time. So, but other ingredients is that, remember, I needed to force the system to enter equilibrium. And that's not a simplifying assumption, so I can make calculations. That's because that's the only thing I know how to identify what the entropy is. Outside of equilibrium, I don't know what the thermodynamical entropy is. So I have to force, so I have to confine the black hole in its thermal radiation so it eventually reaches equilibrium. I have to assume the existence of thermal states, which is far from obvious. It's an assumption. And I need to impose a causality condition, not everywhere, but only in infinity, which I'm okay with because there are no causation violations of causality here because there are black holes in Andromeda. It also turns out there is a relaxation time, much like in statistical mechanics, which is very short for any astrophysical black hole, but it's not immediate. And I need to apply the first law of thermodynamics to the matter outside of the black hole. Keep in mind that this is an open system. It's an open system because there is gravitation. So if you do it, you need to do it correctly. Importantly, there is no commitment of what the dynamical entropy of a black hole is. There are different proposals what it should be based on different preferences. But if you have your favorite and it agrees with with a stationary, in the stationary case, it agrees with the one that we know is right. There is a generalized second version of there is a generalized second law of thermodynamics for your favorite entropy. And interestingly, it selects from all the surfaces, it selects the event horizon, that teleologically defined structure, to be the one that appears in this law. So it's restoring the analogy with the classical area theorem. Okay. No word about the third law, because as I said, it's just an well motivated, but it's just an assumption. Oh, yeah, okay, good. Right, so now I'm just gonna mention some of the open, yeah.
Now, okay. You mentioned that the third law is only an assumption, but isn't there a version of the third law of black hole thermodynamics by Israel in the 80s?
Yeah, I mean, I'm pretty sure he was concerned with this. I'm not sure if I have the same paper in mind, but I know he worked with this cosmic censorship conjectures.
Oh, okay. So you have an extra assumption that you don't want to.
What we know is that it's, for example, the version of the third law that comes from considerations using the Nernst theorem, for example, that says that if you are at zero temperature, you ought to have zero entropy. That's hopeless in black hole physics.
Yes.
Because there are solutions, there are mathematical solutions in which you have black holes, so you have areas, but you have zero temperature, zero surface gravity.
Mm-hmm.
So,
okay, so you are disregarding Israel's third law here because he uses the cosmic censorship conjecture.
Well, I don't quote me on that, but I think he was establishing conditions on which you guarantee that you don't have naked singularities evolving.
Okay, so
if that's
it
so,
has more conditions. It's
yeah,
not
I would
as
say that's
reliable.
more of an endorsement than it is of a proof.
Fair enough.
Yeah.
Mm-hmm. Thank you.
Yeah, no worries. Well, anyway, so let me move into some of the open questions. For that, I'll let me just describe. You may not even believe semi-classical Einstein's equations blindly, but if the matter of fact is that you must agree that there is a positive flux of energy, outgoing, and infinity. Must be, there is conservation of energy, so the black hole must lose energy as a result of that. So if you trust that, the black hole is going to eventually disappear completely, leaving behind only thermal radiation, including that's regardless of how you produce the black hole in the first place. So in particular, you could produce the black hole from a pure state from a quantum pure state, and what you have left in the end is as far as pure as possible. It's thermal. And that's a self-consistent prediction of the semi-classical physics. But many people believe that this conclusion is going to be reversed once you add quantum gravity into the story. And I certainly don't want to get into the rabbit hole of describing many of the proposals there are, but perhaps let me just mention one. Not because it's particularly popular, but just because it illustrates the degree to which the community can be split in this regard. So there was a recent physical review letters by Steve Su and collaborators, and the mechanisms that they believe that the black hole is emitting information out in a way or another is related to the radiation not being exactly thermal, but they are thinking that just like an IO ball that is hot, and if you keep monitoring it and you look at a radiation quantum, there is a conservation of momentum that produces a jitter in a black hole. Obviously, the thermodynamic properties of black holes are very different to those of iron, so that, in particular, that the jittering would get bigger and bigger as the black hole evaporates, unlike the iron ball. But that's something that Steve Su and collaborators take for granted. They think that it is uncontroversial. And for people like myself, Bernard Kay, Alejandro Perez, and Daniel Sudarsky, they had taken for granted the opposite conclusion. Everything is spherically symmetric. So there is nothing that can be responsible for this jittering. And in fact, it looks like it depends on what you're measuring. And it's often the case in quantum physics that if you are precise enough in formulating what you're observing, these problems related to the measurement problem tend to vanish into thin air. That's all I'm going to say about it. But there is a much newer version that physicists like Omhiri, Maldacena, Pennington, Hartman, and others call the information puzzle. But that's a completely different problem. So I much rather use David Wallace terminologies just because it's a different thing. And that we had enough of same names for different things in this colloquium. So I'm going to call it the page-time paradox. And the idea is the following. If I start from a pure state, and I bisect it mathematically and divide it into two subsystems, and calculate the von Neumann entropy of the reduced density matrices, they are identical. And then you can show that using Schmidt decompositions of the original density matrix, for example. So this is pretty well understood. Well, yeah, let me just leave it like that. And there is also the foundation, one of the ways of justifying what we do in thermodynamics from statistical mechanics is by starting from a certain density matrix or probability distribution and setting a set of constraints and looking for the probability distribution that maximizes the entropy given this set of constraints. Then the value of the entropy at the maximum is the thermodynamical entropy. So you've got to have this equality if you believe that that's what's happening in black holes. There is an interior and there is an exterior. So this equation must hold if you had originally a pure state. And the black hole entropy that you see from Bekenstein and Hawking is the process of this maximization. But now we have a problem. Because if you believe the semi-classical approximation, you start from a black hole that has an area, and it disappears to nothing, so it crosses zero. And the radiation has a different pattern. It has the opposite trend. It starts from zero and increases. So the curves must intercept it somewhere. The point of interception is called page time. So what happens is that any time after page time, you have to be violating one of these two conditions. So that's interesting. That seems to be undermining any statistical mechanic underpinning of the laws of black hole mechanics, thermodynamics. And this is all very new. I think this is the oldest paper I've seen with these formulations dates from 2016. There are many proposed solutions. The authors of these papers, they have their own proposal ideas of what's happening here. But let me just remark things that could go wrong. And if you're a bit patient, I'll post it on the archive sometime soon. But there are some issues that must a little bit more careful examinations. First of all, I had mentioned before, these entropies are infinite. It doesn't seem to be a big problem because there are not even density matrices exist in quantum field theory, but there are people like Araki and Roberto Longo. They are doing a very good job in finding well-defined entropies in quantum field theory. So let me not saying that this is a brick wall, but it's useful to bear in mind that this first equality is equality between infinites, as it is. And the second one is, what justifies this procedure of maximization of entropy to obtain quantum statistical mechanics if I know that the original state is pure? It might still work. But you see that the idea of the justification of using this procedure to do statistical mechanics based on the fairest, the most ignorance approach to assigning probabilities seems not to be well-founded in this situation. If you know an application of quantum statistical mechanics, that you do that for systems that you know to be complete, and it works, please let me know. I would love to have an exchange with you. And there is also the problem of identification of entropies. As I said many times, I'm only sure about this identification. Oh, well, anyway, I'm only sure about the identification of the Bekenstein-Hawking entropy with the thermodynamical entropy when the systems are in equilibrium. And the systems are certainly not in equilibrium because the black hole disappears. So let me forcibly make this black hole equilibrate. And lo and behold, they don't cross anymore. So it seems like it's crucial to have outer equilibrium thermodynamics for the page-time paradox to make an appearance. This is not to discredit how interesting it is, but it's just to once again, to make the case that how important it is to understand what out of equilibrium thermodynamics is. Well, not here, but yeah, but I'm forcing it not to disappear, so it reaches another equilibrium, and the equilibrium is such that its entropy is still larger than the entropy of radiation in equilibrium. All right, so one thing that I'd like to say is that it's time that black hole, the gravitational physics, to give back to the foundations of statistical mechanics at least a little bit, at least in the motivations to study out of equilibrium thermodynamics. I said in the beginning that one of the formulations of the second law of thermodynamics had to do with entropy increasing in time. But we all got our degrees in physics without ever applying that the entropy grows in time. All we did was compare the values of entropies in different equilibrium situations set by different constraints, comparing its values, and rarely an equilibration hypothesis, like ergodicity, for example. That's all we need, just comparing between different states of equilibrium. But other applications are more interesting. For example, in astrophysics, there are already models for stars or galaxies that are bound together solely by gravity, and they are unconfined, so they can never reach equilibrium in a strict sense. But people put them in boxes, in spherical boxes, and the models are useful for astrophysics, for the purpose of astrophysics. So it would be very interesting to understand what's going on there in reality. The systems are never reaching equilibrium. Also, cosmological applications of the second law. Roger Penrose made it very popular arguments of relying on the early low entropy hypothesis and gravitational, how gravity might be playing a role in all that. But again, these are highly non-equilibrium situations, and it would be very interesting to know what's going on in them. Finally, this is more from theoretical physics point of view. There are proposals of quantum replacements of energy conditions, the ones that I was referring to as informally as positivity of energy, in which there is an appearance of an entropy. That thing is certainly not thermodynamical. Is there a thermodynamics behind it? And is there a global version of them? These are all local. Is there a global version of them in the same lines that I showed before in black hole physics? There are also entropy bounds. These are global by definition, but they have been proposed for various reasons. And yeah, I mean, let me not say too much about them, but there are many people taking them seriously that say that there is an upper bound of how much entropy you can put in matter. And again, does it have any thermodynamics in it that we can know and say for sure? And with that, I thank you for your attention. And I know that I have not shown full bibliographical details or any of the references, but if you want to know, you can just request it. And thank you.
Questions? Perguntas? Perguntas gerais são aceitas também. I have a question. Can you flash again your transparency on the page curve?
Sure.
Here we go. Okay, so Hawking radiation comes from the collapse of a star into a black hole, right?
Yep.
But here you are assuming that the black hole is already formed.
That's right.
Okay. How would you complete this or change this graph if you assumed that the initial state would be a star in a pure state? Because if the star were in a pure state, the entropy would be 0, right?
That's right, but that's corroborating, isn't it? Because then but the entropy of the matter here is also starting from a very low number.
And then you would not have the black hole entropy, because you would not have a black hole.
That's right. Yeah, that's right. Yeah, but again, at some point you want to be splitting. Okay, okay. I'm thinking this for the first time, but but eventually I'm going to split into something that is inside and something that is outside, and at that point, I ought to have an entropy for both. That's right. Yeah. But I think the argument here. Okay, but that's a very interesting consideration. But I think that's. I mean, there's something to this, even without it, because we project Hawking radiation even for eternal black holes, so these are non-physical. But I could start from a cross-call black hole and believe that there is an entropy for that.
But for eternal black holes, you will not have evaporation, and the entropy of radiation would be constant.
Well, that's true in a self-consistent picture, right? Yeah, that's right. Yeah, but then you believe that you started from something that is an eternal black hole in the beginning, and then you turn on back reaction somehow, and then it starts to evaporate. I don't think this argument has been made that precise enough to be scrutinized in that way, but I wanted to mention it because I think there is something interesting here anyway. Yeah.
Let me follow up on the same question, but I'll speak it in a more technical sense.
Yeah.
In which state does this curve hold? Is it the Unruh vacuum, the Hartle-Hawking vacuum?
Well, it's a state in which you have, yeah, I mean. Well, the problem with the Unruh state is that you won't. It's very physical, but you won't have a 0 in the beginning. But still, you would think that the entropy of the black hole must be much larger than the entropy you have from the matter in the beginning. Just by comparing numbers, right? So the black hole, I mean, with Bekenstein-Hawking in the beginning, that number is huge. So I would think that even though it doesn't start from 0. You should have something like that for the Unruh state, which is the one that better represents the collapse of a star and the formation of a black hole. And it's, yeah, that's right.
Mm-hmm. Thank you.
Alguma pergunta a mais? Curiosidades? Yeah, sim. Obrigado.
It's actually just a clarification question. Yeah. So could you please just restate what's the matter when the mass of the black hole and the level of radiation meet? Like, I'm sorry, I didn't really get it. What happens when...
Yeah, all right. So I want you to think of a point, say, to the right of the page time, right? So it's saying, so you believe that the reason why there is an entropy of the black hole is that there is something, I mean, it's how you decided to bisect your system into two pieces. The pieces the pieces that are inside, the pieces that are outside. So the pieces that are inside has this microscopic entropy that it has to be the same as this entropy, the entropy of the radiation. But what happens is that if they are the same, so the entropy of the microscopic entropy of the black hole has to be larger than the blue curve. But if it is larger than the blue curve, then this inequality is being violated. So the blue curve cannot be describing the equilibrium situation and you get from maximizing the interior in whichever criteria you've got. So that, yeah, I hope it's clear enough.
Better. Thank you.
Alguma outra pergunta? Não. Então vamos agradecer novamente o palestrante. E eu acho que tem algum café aqui esperando por vocês.